Hello everyone, let's talk about fractals. So the goal for today will be trying to understand where this cool looking fractal is coming from, which is called the Mandelbrot set. So Mandelbrot set, yeah. And yeah, but before we can start understanding this fractal, we'll need to understand complex numbers, which are actually not as complex or complicated as people might fear. So very quickly, we need to begin with the real numbers. This is the set of numbers that you're familiar with, like 1, 2, and 3, but also with the negative numbers like -2, -3. And also we have fractions, we have like a half, we have a third, we have 3/4, and so on. And we also have, and so if we only had these, we would have the rational numbers, but we also have the irrational numbers. So numbers like pi, numbers like e, numbers like the square root of 2. So all of these are going to be our real numbers. We usually put them in what we call the real number line. So we have 0 somewhere, we have 1, then we have 2. Somewhere in between we have like the square root of 2, and we have the negative numbers on the other side. And so this is a very nice way to think about real numbers. Complex numbers, on the other hand, they try to solve a question, which is, or well, a problem with real numbers. And the thing is that in the real numbers we can split some polynomials. So x squared minus 2, we can split this polynomial into x plus the square root of 2 times x minus the square root of 2. This is some splitting that we can do in R, but we cannot do it over the rational numbers. And it turns out that we can split a lot of polynomials in R. We have almost everything we need, except we don't have everything we need. There are some polynomials like x squared plus 1 that we can't split in R. So they have no real solutions. And so the question is, can we artificially create a solution for this? And this is what the complex numbers are all about. We say, we let I be a number, whatever number means, such that whenever I write I squared, I replace it with -1. And so in a way we are artificially creating a solution. So we can split x squared plus 1 as x plus I and x minus I. Because, well, if we have I squared is equal to -1, this implies I squared plus 1 is equal to 0. Okay, so then the question is, what are the complex numbers? The complex numbers are numbers of the form a plus bi, where a and b are real numbers, and I is this number we've more or less created. And the idea is that if you have numbers which are real number plus real number times I, if you add them together, you still have a complex number. If you multiply them together, you get something interesting, which is still a complex number. So a plus bi times c plus di. Well, we can expand this, right? We can write this as ac plus adi plus BIC, which I can write BCI, plus BI times DI, which should be BDI squared. But we know that I squared is something that we replace with -1. So this is going to be equal to AC minus BD, because we have this -1 here, plus AD plus BC I. We just factorize the I. So if we multiply two complex numbers together, we still have something that is a real number plus a real number times I, so we still have a complex number. We can do something similar for division by noticing that, well, if a plus bi times a minus bi, that should be equal to a squared minus b squared I squared, which is equal to a squared plus b squared. So if we rearrange, we get that 1 over a plus bi. So essentially we move this to the other side of the equation, then we need to move this to the other side of the equation, is equal to a minus bi all divided by a squared plus b squared, which I can write as a divided by a squared plus b squared minus b divided by a squared plus b squared I. So once again, division is just a real number plus a real number times I. Yeah. Okay. So then we understand that complex numbers are just numbers that we can add, we can multiply, we can divide together, which is nice. Can we visualize them though? And for the real numbers, we had the real number line, right? Where we had 0 here, we had 1 here, we had -1 here. And so the idea is that for the complex numbers, we can do what is called an Argand diagram. And so we have the real axis and we have what we call the imaginary axis, where we have the number I, but we also have -I, for example. And in this Argand diagram, we can find all of the complex numbers, such as, for example, I plus 1 would be here. It's a bit hard to tell, but this Xaos is an Argand diagram. So here would be the real axis, here would be the imaginary axis, 0 would be somewhere around here, 1 would be around here, -1 would be around here, sorry, around here, 2 would be around here, and -2 would be around here. But we'll get very soon to how we get this cool looking shape. Because for that we will need to talk a little bit about sequences. So a sequence is just a number followed by another, followed by another, followed by another, which I'm going to call Z0, Z1, Z2, Z3, and so on. Some sequences we can define like, I don't know, Zn is equal to n. So that would be like 0, 1, 2, 3, 4, and so on. But some sequences we can define based on the previous element. So we can define Zn is equal to Zn minus 1, the previous number, plus 1, for example. This does give us the same exact sequence if Z0 is equal to 0, right? And so the sequence we're going to look at is Zn is equal to Zn minus 1. So every number is going to be the previous number squared plus a constant c. And this constant c is actually going to be Z0 for now. This will change later, but in a second. So let's just look at some examples. So what happens if Z0 is equal to 0? Well, 0 squared plus 0 is also 0. And if we square 0 again and add 0, we still have 0. We square 0, we still have 0. So this is a very interesting sequence. What happens instead if Z0 is equal to 1? Then we begin at 1. 1 squared plus 1 should be 2. 2 squared plus 1 should be 4 plus 1, which is 5. 5 squared plus 1 should be 25 plus 1, which should be 26. 26 squared plus 1 should be, let me take my calculator, so 26 times 26 plus 1 is 677. And if I square that, and that 1, I get a really huge number, so that's 458,330. And so as you can see, the sequence can sometimes stay nicely around 0, or it can just blow up and get bigger and bigger and bigger and bigger. And so the question is, for which numbers does this happen? Let's just look at a few more examples, which will be relevant. So another example would be z0 is equal to -1. -1 squared is 1. -1 gives us 0. So -1 squared minus 1 should be 0. 0 squared minus 1 should be -1. -1 squared minus 1 should be 0. And so this is another sequence. And this one, it's interesting because it doesn't stay fixed. It always alternates between two numbers, but it doesn't blow up either, which is nice. Another example that is interesting is z is equal to -2. -2 squared is 4, -2 should be 2. So even if we start at -2, we then fall into 2. 2 squared is still 4, -2 is still 2. This means that once we reach 2, we just stay there. Yeah. Okay. And the last real number that is going to be interesting is going to be z0 is equal to a quarter. Because we begin at a quarter. A quarter squared should be an eighth, plus a quarter should be 3/8. 3/8 squared should be 9/64, plus a quarter should be 9/64 plus 1/4 should be 25/64. And this is a number that is getting closer and closer to a half, but it never reaches a half. So it's quite interesting. Why is that the case? The thing is that if you begin with something that is less than a half, so if zn minus 1 is less than a half, this means that zn minus 1 squared is going to be less than a quarter, because a quarter is a half squared, and this is assuming that these are positive numbers. And this means that zn minus 1 squared plus a quarter is going to be still less than a half, which is like a quarter plus a quarter. So just take this equation, add a quarter on both sides, and get that zn is less than a quarter, but it's still positive. Yeah, so this sequence is never going to reach a half, and so it is once again bounded. And just as a little bit of spoilers, if we look at this argand diagram, I mentioned that 0 is around here, -1 is around here, -2 is around here, and this number around here would be a quarter, which is this specific interesting number. But we have learned about the complex numbers, so let's just do a couple of examples with I and minus I. And so the idea is that if I start with I, then what is I squared? I squared is -1 plus I should be I minus 1, right? What is I minus 1 squared? So I minus 1 squared plus I should be equal to, well, I squared minus 2I plus 1, just expanding this, plus I. And this should be equal to minus 1 minus 2i plus 1 plus I. And there are some cancellations, which gives us the minus 1 and the 1 cancel out, the minus 2i and the I cancel out to minus I. But then, what is minus I squared plus 1? Sorry, plus I. Well, minus I squared is still minus 1, so that's once again I minus 1. So the sequence goes I minus 1, minus I minus 1, minus I minus 1, and so on. I would be around here. And so once again, the sequence stays bounded. And you can do the same for z0 is equal to minus I, and you find that this point here is bounded. So this is the Mandelbrot set. It is the points in C such that the sequence Zn is equal to Zn minus 1 squared plus C, where C is equal to Z0, remains bounded. And in particular that it doesn't blow up to infinity. And one thing you can show, and which we will not show today, but you can show that if the absolute value of Zn is greater than or equal to, sorry, is strictly bigger than 2, this absolute value is defined as the square root of a squared plus b squared if z is equal to a plus bi. Which, if you remember the arcane diagram, this is basically how far we are from the origin in terms of radius. And so the idea is that if this Zn ever is bigger than 2, then we know it blows up. And so that is precisely what we do when we are painting this fractal. And this calculation, let's just do one iteration. And so what we have is just a black squared with another one here. And so it's just telling us, well, everything here is less than 2, everything here is bigger than 2. But now if we increase the iterations, we're looking at the things such that Z1 is already bigger than 2. Because if Z1 is bigger than 2, we know that the sequence will blow up eventually, right? So for example, here would be 1, and we know that 1 squared plus 1 is equal to 2. And so 1 will already be, we know that it will blow up, so we remove it from our set. Our set is going to be what remains in black. And so if we increase the number of iterations, now these are all the things such that Z2 is bigger than 2 are the new things that have been removed in here. And so we just keep removing more and more. And so the Mandelbrot set itself is everything that is in black. So everything that is not removed. Every color layer is telling us how many iterations. So what Zn is the first such that it is bigger than 2. Because we know that if it ever is bigger than 2, through this theorem that we have actually not proved but that we will trust in, if this is bigger than 2, we know that it will escape. And so we color things based on how long it takes it to escape. And what's crazy is this is Zn is equal to Zn minus 1 squared plus 1, sorry, plus C. This is a really, really simple formula. And we get this crazy looking fractal. Sorry, I'm going to increase the zoom speed to twice. And it has some crazy details. So if you zoom in, you will start to see that there's like little fractals that are self-similar. If you zoom in more, you get another little Mandelbrot set over here. And if you zoom more, it just gets crazier and crazier and crazier, right? And so the complex numbers are amazing in that a very, very simple formula gives such like interesting results, right? Okay. So now we understand the Mandelbrot set, and we understand Xaos, really. So Xaos is just painting sequences. And so we have sequences, and we have an escape, which is when Zn is bigger than 2. Right? And so all it is doing, it is painting the color based on how long it takes to reach that escape. So let's just do a very silly formula. So what happens if we have z, I don't know, plus 1. So when I write z plus 1 here in the user formula, this means Zn is equal to Zn minus 1 plus 1. What do you think will happen? Well, this is what happens, I guess. Wait, no, that can't be right. Fractal. We need to initialize this, I think. Because otherwise it is always initializing to z0 is equal to 0. Now we just said like z0 is equal to z, right? And so if z0 is equal to z, then everything in here will be 1. So we'll be outside after you add 1. Whereas everything here you need to add 1 twice before it gets outside of the circle. Everything here you need to add 1 thrice to get out of the circle, and everything here needs to add 4 times before you get out of the circle, right? Another interesting formula would be just z squared, right? Z times z. And so what we get is this circle. And why is that the case? So the thing is that, well, if a number is bigger than 1 in absolute value, so if z is bigger than 1, then this becomes z squared, z to the power 4, z to the power 8, and so on. And this is growing more and more and more, and eventually it will reach 2. But if z is less than 1, then when we take z squared, that's a smaller number. When you take z to the 4, that's even smaller. And so it's converging to 0. So everything inside of the circle is getting closer and closer to 0, whereas everything outside of the circle of radius 1 is going towards 2. And if we get closer, we see that there's more and more layers, because there's going to be numbers that take a long, long time before they actually escape the 2, right? Yeah. Okay. So let's just double check that the z times z plus c is our indeed favorite Mandelbrot set. And again, we were zooming in around 1, so let's zoom out, and there we go. Here's our Mandelbrot set. So we have the Mandelbrot set. Can we do something similar that is also quite nice looking? And the answer is yes, we can use what are called Julia sets. And the idea is that we still have Zn is equal to Zn minus 1 squared plus c, but now this c is constant. And it doesn't depend on the initial point. So maybe c is equal to 1, maybe c is equal to 2, maybe c is equal to 0. And so what we do is we could write that in the user formula. I could just replace this c with a specific number. but I can do what is called using the Julia mode, which is by pressing M here. So if I press M, it changes C from like the point to a fixed C for all points. Yeah, so this would be, if I press M around here, it would be what happens if I replace it with 1. And if I do it around the center, we get a circle that is looking very much exactly like the Zn equal to Zn minus 1 squared example we were doing, because that's exactly the same as Zn minus 1 squared plus 0, right? But what's interesting is what happens when we choose points that are close to the edge. Well, let's just look at minus 1 first, because that also looks pretty cool. And near minus 2 we get something like this. Near I we get something like this, which looks really nice. But if we go near the edge is when we start getting some really cool stuff as well. And depending on where we do it, we get different Julia sets. And as you can see, Julia sets are much more symmetrical than the Mandelbrot set. The Mandelbrot set does have like a lot of cell repetition. So for example, this is like the big one, but then there's a small one here. But if you look at a Julia set and you zoom in, it's going to look very similar to what you zoomed into, right? Yeah, okay. And so another thing that is quite interesting to know is what happens when you zoom in. Well, when you zoom in, the numbers in the Mandelbrot set, Zn is equal to Zn minus 1 squared plus C, these numbers are going to be very close together. So the closer you zoom into the Mandelbrot set, the more it will look like the Julia set. And so let's just do a couple of examples. So calculation, zoom speed, let's increase that to 5. So let's zoom in here, right? Okay, maybe around here. If we press M here, then we get something that looks similar, but all around everywhere. If we look maybe around here, and I press M here, it almost looks like I just rotated the thing, right? But if I zoom out now, I see that I actually have a Julia set. If I zoom in, let's say around here, again, it looks like a rotation, right? But if I zoom out, now I have the Julia set. Okay? And so when we are exploring fractals, what we can do is write a formula with a plus E, and then just press M around to see what we get at different points, right? Okay. But this Mandelbrot set is very cool and all, but we want to create our own fractals. So how do we do that? Just go to fractal, use our formula, and we create our own formulas. But then how do we make interesting formulas? One of the first things we can do is try, well, what happens if instead of z squared we have z cubed, right? And what happens is it now looks like we have like two bulbs in the Mandelbrot set. But now all of the Julia set will have triangular symmetry. And so if I do it like here, I have like a little triangle there. If I do it around here, I get another triangle. If I do it around here, I get another triangle. Yeah. Can you guess what happens when we take z to the power 4 plus c? now the Mandelbrot set itself looks kind of triangular, but all the Julia sets are going to look squarish. Yep. The next thing we can do is use power series. So we know that what is a power series that you like? Maybe you like sine of x, and that, sine of z is going to be a power series that begins with z minus z cubed over 3 factorial plus z5 over 5 factorial, and so on. And so sine of z, if we ignore the bigger terms, looks kinda like z. And so z squared is going to be kinda like sine squared, or like sine z times z, or like sine of z squared. And if we try any of those, we should get something that looks kinda like the Mandelbrot set. So if we take sine of z squared, we get this, which doesn't quite look like the Mandelbrot set right now, but that might be because of the 2 bound that we have, so we're going to exchange that. So the bailout, instead of being 2 squared, which is 4, now it's going to be 16. And so we get a really cool kind of fractal, but it's kind of like very horizontal. And if we zoom in, this looks like a Julia set. So the Julia sets looks like Julia sets. So this was sine z squared. What about z times sine z? Now this one looks a little bit more like the Mandelbrot set. And you still get really cool things going on. Yep. Another thing we can do is use logarithms. So the key thing to understand about logs of complex numbers is that it's not exactly the most well-defined kind of thing, because there's several different, so it's a bit like the square root, all right? So the square root of x, the square root of 2, like it could be either, what's it called? Well, it could be a square root of 2, but it also could be the square root of minus the square root of 2. Both of these numbers, when squared, gives us a 2. And what happens with the complex numbers is that if you try to make one function that is the square root of 2, you can begin here and extend it, but by the time you get back here, you're now, instead of having root 2, you're having minus root 2. So what that means is that for your functions, you need to define like a cut. And so let's try to do that. So my user formula is now going to be z times the square root of z. And so this square root is going to have a cut. And this cut is something that we are going to start to see in the fractal itself. So this is the cut that is happening because of the square root function having this cut. And so when we start looking at different Julia sets, these Julia sets will have these cuts, which can be quite nice looking, or can be like something you might not be looking for. This looks like a little worm, which is nice. And again, similar to the square root, the logarithm also has a cut. Okay. And so we similarly have like the cut over there. Even we can have some very interesting, and even things that look like what we were getting with the Mandelbrot set, right? Just now with cuts. Yeah. We can also start looking at things like using the exponential. So let's just double check. So what is e to the x? So should be 1 plus x squared over 2 plus x cubed over 3 factorial and so on. So what we can do is, I don't know, the exponential of x minus 1 should be something that begins with x. So we can take that squared, or we can multiply by x to get something that begins with x squared, right? So let's try z of times the exponential of z minus 1. So we once again have something that looks kind of like a Mandelbrot set, but quite different in some quite interesting ways. Yeah. And so this is how we can get formulas that start looking like the Mandelbrot set. But there's some other crazy formulas you can start working on that have nothing to do with the Mandelbrot set. Just combining exponentials, logarithms, sines, cosines, fractions. Like for example, let's see what happens if I don't know, we have a fraction, so we divide now by z minus 1. So that should gives us, like, it should blow up around 1. And if we do something like z times z, so we get something that is blowing up around here. And it's giving us some rather interesting results. Kind of like in a sequence, I guess. Yeah. Well, I think this is enough for today. I will leave you to explore fractals. There's tons of formulas that are already written, but I think the most fun thing is creating your own formulas. I will just leave you with one last final formula, which is my current secret formula, which is z squared minus p squared plus c. And the question is, what is p? And the answer is in this, so z refers to zn minus 1, p refers to zn minus 2. So this is the formula: zn is equal to zn minus 1 squared minus zn minus 2 squared plus c. And this is a quite interesting fractal because it looks like a little fish. The Julia sets are also pretty crazy. I mean that you get like, we're getting so many colors, which means that these numbers are like taking so long to get outside of the radius. Which is something you don't get for many fractals. You get some crazy looking things, which can be quite nice. Okay. Yeah, this would be the end. Thanks for watching.